Hello, that was super interesting so far. So my name is Huib Kleinhout. I'm a product manager. I'm working at Google, working on the WebRTC team. This is Olga, who is leading the Chrome audio efforts, and we'll talk more about what they've done there. And then there's the founder and eng lead, Justin Uberti, who you hopefully know all. So I'm kicking off. This has been super interesting, and we see within Google, we use WebRTC all over. We use it for YouTube live streams, for making duo calls, for Hangout meetings, in home devices, up into self-driving cars. And we're not the only ones. We see like that the ecosystem continues to grow a lot. More than 50% growth in audio and video since last year, even more in the data channel. This is petabytes, billions of minutes weekly. And this is only a fragment of what we can measure based on anonymous usage reports within Chrome. So there's at least a tenfold more in the whole ecosystem. So things are going really well. And with this growth, with the growth of the ecosystem, we're transitioning from a demo that works on your machine to something that everyone here like builds their business up on, makes frameworks on, that not just need to work once, but need to work every single time. Where the APIs need to be stable and predictable, and the media needs to be reliable and high quality. We worked a lot on that with WebRTC 1.0. So the API piece, we start to look good now. So we have like two sets of APIs, one set governed by the W3C body, and the other by the protocols by the IETF, and those are reaching stable status now. So the main APIs on microphone, camera access, peer connection, they have reached candidate recommendation state now, meaning that no major changes are coming and the protocols are finished, finished as they can be. The RTC Web working group actually also paused its activities for time being. So that is looking good. And the browsers are also becoming more compliant. We see all the web browsers have increased their compliance score over the course of the past years. They're reaching levels that is normal for web standards. You can see like that we're looking really good for microphone and camera access, and peer connection is ramping up as well. Microsoft Edge, there's still some automation to do, but there's also good progress on that side. Meaning that's like the APIs that are spec'd out there, they're actually implemented and they work. Within Chrome, we worked a lot on the second part, making sure that media is reliable and of high quality. We have had two major projects that are landing right now and becoming part of the default in Chrome. First is a new echo canceller, AC3, which is not only better, but it's like in our measurements, we see that you're 10 times less likely to get echo with this new echo canceller, and it even works better than state-of-the-art echo canceller that is built in macOS for MacBooks. So it works really well. This means you'll have echo-free conversations. So a lot has happened in the past 2 years. All those basic APIs, part of WebRTC spec for transceivers, receivers, senders, unified plan SDP have been added, and we did a lot of under-the-hood work for making reliable and echo-free, glitch-free audio, with these major projects landing early next year. And this is not only in Chrome. In Safari Technical Preview, we're also very excited that VP8 has become available as one of the video codecs, so you have true choice as a developer. Safari also switches to Unified Plan by default for their SDP format. And within the industry, we agreed on extensionless screen capture, or how to capture the screen with get display media, coming to all browsers as well. In the meantime, we continue to address pain points within developer-facing APIs, such as the MDS as a solution mitigation for privacy-sensitive APIs, and getting like better, more robust simulcast APIs. But within Chrome, we're very excited that H.264 for simulcast will land the next Chrome release, and will become available using standard APIs. So we're getting there. We address all these pain points, which hopefully help to application developers to avoid having to make custom WebRTC versions that fall behind and that are susceptible to security problems, and that you can use these standardized APIs to innovate for your applications. And with that, I'm taking it to Olga.
Thank you. So the mission of our team is to deliver best possible WebRTC audio quality. And so what do people need to know about car engines? Generally not that much, because if you are not a mechanic or if you are not an engineer, but if you know basics, that it probably will make you a better driver. And Chrome is a big car which delivers WebRTC experience to the users. So we'll dive in audio part of the engine of it. So we'll talk about how audio works and WebRTC in Chrome, and what are the challenges and the improvements which are coming, and there will be some practical advices on the way. So I'll touch a bit on WebRTC audio processing and on Chrome architecture for audio, and then how they fit together. So what's happening with audio in WebRTC call? We receive our audio signal from the microphone, we encode it, we convert it to RTP packets and send out to the network. And then we also receive from our peer, we receive RTP packets, depacketize, decode them, and play out to the speakers. And in ideal situation, our peer should hear only our voice. But what happens is that microphone signal got picked up by, speaker signal got picked up by the microphone. If we do nothing, then it's got transferred to the remote, and our peer will hear their own voice with a delay, and it's perceived like echo, and it's very annoying, and it destroys communication experience. But as you can see, actually, if our peer hears echo, the problem is on our side. And so we need to do something to prevent it, and this prevention is called echo cancellation. So we know which signal we are playing out. The signal which is picked up by the microphone is not exactly the same, because it's modified by room acoustics and by device characteristics, but we kind of probably can guess what it is. And if we guess correctly and remove it, then the peer will hear perfect audio without echo. But to do that, we also need to know this delay, because there is some delay between the play out signal and it gets picked up, so we need to estimate this delay. But the thing is, if this delay varies a lot, if it jumps, we are falling behind with these estimations, and then echo will leak. So stable delay is very important for effective echo cancellation. A component in WebRTC which does echo cancellation is called acoustic echo canceller, and it's a part of audio processing module. It's here, and I'll talk about the whole audio processing module. It's not really separatable. So echo path stability matters, and when you hear an echo, the problem is on the other side. Now to Chrome audio. Security is a key principle of Chrome architecture, because user needs to be secure when browsing web. So the main concept of Chrome is multi-process architecture. We have main process called browser. It runs UI, it manages other processes, and it's a privileged process. It has access to all the devices. And we have a bunch of renderers, which roughly one render per browser tab. And they deal with all untrusted content. They parse HTML, they run JavaScript, etc. And since the content is untrusted and is dangerous potentially, so they are sandboxed, which means they are not allowed any system interactions, and the only interaction they are allowed is a predefined set of IPC communications with the browser process. So according to this concept, all access to audio devices also lives in the browser process. And we access devices through platform audio libraries. They're different on different platforms, and they work on top of drivers, apparently. And this is also third-party code for Chrome. And it's not always performing very well. Like, there are problems with drivers and sometimes with platform as well. And it is very hard to fix for us because we don't own this code. So a couple of problems associated with that. First, platform audio can hang. And then the only way to restore its operation is to restart the whole browser. And this is a frustrating user experience. Actually, Chrome monitors microphone for hanging. And if hang is detected, then Chrome issues media stream track ended event. So application can process this event to notify the user that there are problems with microphone or with audio stack. Another issue is that platform audio can crash. And if it crashes, it means main process crashes and the whole browser instance crashes, which is also a super frustrated user experience. So this is our first security trade-off. We have platform audio running in the main process, so we have hangs and browser crashes because of audio drivers. Now, how render accesses? So we have render in sandbox, we have browser with all access to the devices, but how render gets a chance to communicate with these audio devices? So for capture, we just get user media. Standard cases, platform audio runs a real-time thread driven by the sound card, which receives audio buffers from the microphone, and we want to transfer them to the render side and to media track. So we have a corresponding thread on the render side, and we pass audio data over IPC using shared memory and sync sockets. And for capture, which is media tags and audio context from web audio, we also have real-time threads driven by the sound card, which request audio buffers from us. And we have corresponding thread on render side to pull audio graph and pass audio data to the browser process and to play it out. What's important here is actually each audio stream set up like that has two threads, and they're real-time in the render and in the browser. So one in the render, one in the browser. So if we have many different audio streams, we have twice as many of these real-time threads. And real-time thread means high priority. So if we run not on a very powerful system like 2 cores, 4 cores, or if system is under heavy load, if we have many high priority threads competing for CPU, it creates a lot of performance problems. So applications should use audio streams with caution if they care about low performance systems. And actually on Chrome Media Internals tab, Chrome Media Internals page, on audio tab there, you can check how many audio streams are running now. There are input controllers, output controllers, and each of them represents audio stream, which is 2 real-time threads, so you can count them. So we have a second security trade-off. Render runs in sandbox, so we have 2 real-time threads per 1 audio stream. Now, the WebRTC audio in Chrome. The WebRTC works on untrusted content received from the internet. So, and it does a lot of math there. It decodes, it processes audio and processes video, a lot of stuff going on. So it must run in the renderer. So this is our Chrome multi-process model and audio pipes set up and access to audio devices. And network accesses are also in the browser process because only browser process has access to the devices. And this is our WebRTC with playback, capture, and network. And this is WebRTC in Chrome. So we basically introduced a bunch of IPC communication there. Now let's look at this echo path, which is important for us to be stable. We have 4 threads on the way and 2 IPC communications, which means it's subject to scheduling issues. And if system is under heavy load, for example, this delay will be unstable. Or if we have a lot of high priority threads competing for CPU, this also will be unstable. And we'll have echo cancellation issues. Yeah, so that is our third security trade-off. We have audio processing in the renderer, and we have long and unstable echo path. So we'd like to shorten it. How would we do it? Let's, for a second, imagine that audio processing is moved to the browser process. And it looks kind of much better because we have only 2 threads now. We don't have any APCs. Looks good. The problem is, according to Chrome security principles, we can't do that. We can't run operations on untrusted data in the browser. OK, and what if we extract all audio stuff and move it to a separate process and then move audio processing there? Can we move it? Can we do that? So it turns out we actually can do that with a set of conditions. So first, we need to sandbox the process, and then we need to make sure it works safely as much as we can on all sorts of data, valid and invalid. And another benefit, actually, of having this separate audio process is that if it crashes, for example, or if it hangs, the rest of the browser survives. So we can then restore the process and continue operating normally with audio functioning. So how our audio process looks like with our security trade-offs. First, we moved audio from the main process, which means we are doing much better in terms of hangs and browser crashes because of audio problems. This one kind of didn't change. We still have 2 real-time threads per audio stream, but also we moved audio processing much closer to the devices, to the audio process. So we stabilized delays. We made echo cancellation path shorter, echo path shorter. So it looks good. We should go for audio process. How would we do it? Chrome has Mojo framework, which is IPC framework. It's a set of IPCs which allow interfaces to communicate with each other in a process-agnostic way. So when 2 interfaces talk to each other, they don't care if they're in the same process or if they're in separate processes. And on top of that, we have Chrome services. So each service is a coherent set of Mojo interfaces with the implementation. And there is a service manager which manages them. And it can run a service in the browser process, or it can run it in a separate process if we ask it to do so. And the rest of Chrome won't even notice because it's Mojo, it's process agnostic. So it's all very simple. We should first wrap all audio functionality into Mojo service. Then we need to move it to a separate process. Then we need to sandbox it with exception of access to audio. Only audio should be allowed there. And then we can have audio processing in it and have all the benefits of having this separate process. So problem solved. Well, it turned out to be not very easy. Our current state is we have audio process on desktop platforms. It's still an experiment because we don't want to break everything, so we are seeing some issues, so we are fixing them. And we are aiming to launch audio process in M71 and audio processing in it in M72, which are Chrome releases. And you can try it out right now, passing this fancy set of parameters to Chrome command line. And you can double check in Chrome Media internals, but that's starting from M71, that all parameters are correct. And then if you go to Chrome Task Manager, you will see a process which probably you won't see now. It's called Utility Audio Service. And you can press this End button, and then it will be killed. And if you are playing audio, it will stop playing. And then you can reload the page and play audio again, and this process will be relaunched. So you're welcome to file bugs. You're welcome to read design doc and check the source code. And now just takeaways. So security is important fundamental principle in Chrome. We can't just step over it. So and audio has some difficulties with that, but we are mitigating it. When you hear an echo, the problem is on the other side. It's not your problem. One audio stream means 2 real-time threads, and they should be used with caution. Media stream track exit event is very useful to process. Actually, with having audio process, it will be more useful, even more useful, because if process crashes, you will also receive media stream exit event. Soon it will be possible to restore audio in Chrome without restarting it. And echo cancellation will be improved. And now, yeah. Now to Justin.
All right, I just wanted to say, thanks to Olga. That was a great presentation, and I want to just stress the fact this represents really 10 engineer years of work, probably even more. Like one of the biggest infrastructure projects we've ever taken on. We're now getting close to like fully rolling this out, and as she demonstrates, it's going to have significant benefits in audio stability, especially when the overall system's under load, and significant improvements in echo cancellation, even on top of the AAC3 improvements that Huib mentioned. So once again, this is tremendous. Thanks, Olga. All right, so that is sort of the present, and now let's talk about future of WebRTC. So there are a few different things here that are going on, and WebRTC NV is sort of like the umbrella term that we use to refer to like what is the next generation of WebRTC. And it's a bit of an umbrella term in that you can put a bunch of different things into this sort of box of what is NV. It's pretty much anything that isn't being done today could be considered NV. But where we actually see actual sort of momentum occurring and people kind of gathering around things is on these three main topics. The first, around more direct, lower-level control of the actual WebRTC sessions and media. The second, around alternate transport protocols. In the ITF, Quick has really taken on a lot of momentum, a lot of things happening there around using Quick for HTTP, and people starting to think about where else can we use Quick. In media is one particularly interesting example. It would be wonderful to have a common client-to-server and client-to-client protocol. And then on AV1, AOM, the overall consortium for the Alliance for Open Media, has come up with AV1 as a unified codec, and it has broad support across the industry. We're seeing implementations start to come out, and we're going to start to see them be tuned for real time in the not too distant future. And so these three things are all like very exciting, and will all give us a lot more capabilities in the WebRTC space. But in particular, I want to talk about the low-level APIs today. So the web sort of started off as a declarative platform. It's documents. It's written in HTML. And then Brendan Ike got the idea saying, what if we jammed on like a scripting language to like that platform? Couldn't we do some really interesting stuff? But the web sort of grew up as, OK, let's start with documents and then add a little bit of programming functionality. And for a variety of reasons, the type of APIs that existed on the web were sort of aimed more around people publishing documents than writing large software applications. And this kind of resulted in a bit of a bias toward high-level APIs. And high-level APIs are wonderful. It's very easy to learn a technology. You can grab a code sample from Stack Overflow, plop it in, off you're going, and your thing is often doing like magic. And XML HTTP request was one good example of this. But it has some trade-offs. They're easy to learn, these APIs, but if you find the API doesn't do exactly what you want it to do, there's no really ability to customize it or to go underneath or to like, deal with like browser-to-browser variations. And WebRTC as a working group kind of struggled with this. Where do we want to be on the API spectrum between high-level declarative APIs and low-level super customized every single knob type thing? And there are even proposals in the early days of WebRTC to say, let's just have SIP in the browser, and basically the API will be make call to, and you provide the address. On the other hand, there are some proposals for Microsoft and others of basically doing everything down to individual ICE timing checks in the browser. And we ended up with like a middle API, and one of the reasons we didn't go lower was that if you have a super low-level API, that basically means if you want to do anything, you have to write a lot of code. And since it's JavaScript, it meant that you really couldn't easily translate existing code that maybe you had for a desktop platform into the browser and start running that. And so that sort of mix of really, really complicated APIs plus start over from code standpoint made it really difficult to get low-level APIs off the ground. So enter WebAssembly. So suddenly, we have this ability to run C code in the browser, and it's really supported across the entire web ecosystem in every browser. And internally, we kind of think about it as like, this is the NDK from like the Android scenario, native development kit for the web, where you can take that code that's written in C, that's tested, that's running in other platforms, and bring it to the web. But one thing we didn't know was what were the performance characteristics of this going to be? Could you actually do video processing? Could you actually write like video codecs and deploy them in WebAssembly? And so we were kind of scratching our heads about this, a couple months ago, when suddenly Philip Hankey made this discovery that Zoom.us, any Zoom folks in the house here? Willing to let yourself be known? basically found out they're not using WebRTC in their web version of their conferencing app. They're actually doing video encode, well, at least video decode, and audio encode and decode in WebAssembly, and then they go and take those bytes and stuff them over a WebSocket to be sent to their conferencing server and interact with the other endpoints. And I assume the reason for this is because they have some very specific sort of functionality they need to interoperate with their other endpoints. But basically, it was pretty clear, we had an existence proof, that you could do heavy lifting, video encoding, audio processing, all in WebAssembly. And this is with, really, the APIs had not been tuned for this purpose. This was with the existing APIs, with WebSockets running over TCP, with no, really, deep control over timers or threads in WebAssembly, with really no debugging tools. They had been able to do this. So basically, it's like, if you can make it work with this, imagine what you could do with some really tailored, specific, low-level APIs for WebRTC. And so this is where we started thinking, OK, what stuff could we start doing if we happen to have these low-level type APIs? And one of the things is all right, let's do some audio processing. And we thought, hey, let's go out and find some existing audio processing algorithm that seems kind of interesting, and compile it to WebAssembly, run it in WebRTC, and sort of see what happens. And so this RN noise thing was something done by XIF, where basically they have a deep neural network that tries to identify what's speech and what is noise. And anyone who's ever used a conferencing application that has speaker switching will know that sometimes all of a sudden the camera will just cut to somebody and they'll be eating or scraping their plate or dropping a knife or something like that. And that's because actually doing voice versus speech versus noise separation using a heuristic is kind of notoriously inaccurate. So if you use a deep learning approach, we can probably do something a lot more interesting. So we thought, hey, let's go try this out, plop this existing C code into WebAssembly, run it, and see what the results are. So let's do that right now. OK, so here I'm talking, and the red line you see up here represents the speech probability. The blue line over here represents the noise probability, and since I'm speaking, it's pretty clear that there's not a whole lot of noise. But let me change that. So as I start making noise, you now start seeing the blue line go up, and now as I start speaking again, the red line starts returning back to its original position. And this is a bit of a contrived sample. Again, I wasn't sure how well it's going to work here in an audience where there's a lot of noise, and I'm speaking through a microphone and everything. But now we're taking off-the-shelf code that's tested code, and you can plop it right into the web, and now you have these full capabilities in the application. That was a dry chip. Anyway. So, fortunately for me, you get the idea. OK, so what do we want to do? Provide developers like you who all know how to do really complicated stuff and give them the sharp tools they need to really, A, provide lower-level access to the media network so you can take the code that you're already running on Android and iOS and deploy that in the browser as well. And the APIs that we're going to provide are going to be more similar to the type of APIs you're already familiar with on Android and iOS. More similar to things like Video Toolbox or Media Codec. We won't be giving out raw sockets, but we'll be going almost like the next level up. And so what this means is you'll have more application code running and less implementation code. And so in addition to reusing your own code, you also have less variability between browsers. That there's less stuff that is different on the implementation because more of it is your code. And what does that mean? There's increased ability to differentiate and increased ability to innovate. And so these things all, if you look at the graph on the right, the stuff that's all in green is being done currently by peer connection, as is the stuff in gray. And with WebAssembly, we can take the stuff that's in green and put that in the hands of you, the application developers. And so we have new exciting ideas about what codecs you want to run, what you want to do with media processing, and what you want to do even with adaptation around things like FEC, RTX, those types of things for which handle like different networks that can all be in the hands of application developers. So I'll just wrap up now. The overall takeaways, though, is that, again, another great year for WebRTC, continued strong momentum, as Olga shows. The last pieces are falling into place, AAC3, the new audio process, and lastly, WebAssembly and these new low-level APIs are going to provide us with a bunch of powerful new tools that will let you all go out and create the next great things in the WebRTC ecosystem. Thank you.